We are going to start going through section 4.5, which is about rational functions. So we're going to start off with our definition of rational functions. A rational function, f of x, is equal to the ratio of p of x divided by q of x, where p of x and q of x are both polynomials, and q of x, the polynomial in the denominator, is not equal to 0. So there are several things that we're going to talk about with regards to rational functions. We're going to talk about the domain, we're going to talk about intercepts, we're going to talk about removable discontinuities, holes, we're going to talk about asymptotes, and then we're going to bring all of those pieces together and talk about graphing and actually do some graphing. We are going to be covering all of these pieces today, and then tomorrow we will focus on graphing. So those first three things that we're covering today, domain, intercepts, removable discontinuities, we've talked about all of those pieces before, so we're going to do kind of a brief review of those, and then we'll spend most of our time today talking about asymptotes. Domain for a rational function is everything except where q of x, our denominator, is equal to 0. So what I want to do here then is I need to factor this denominator so that I can find its zeros. Let's see, if I factor that denominator there, multiplies to 15, adds to 8, that would be 5 and 3. So x plus 5, x plus 3. We're not worried about the numerator, so I'm just going to recopy that. So the zeros of my denominator then are negative 5 and negative 3, which means x can't be equal to negative 5, x can't be equal to negative 3. It can be any other value except those two. So when I go to write my domain using interval notation, we can have any kind of negative number all the way up to negative 5. We have to leave negative 5 out, so I'm going to need a union. It can pick up on the other side of negative 5 and go all the way to negative 3, but then we have to leave negative 3 out as well, so I'm going to need another union again. It can pick up on the other side of negative 3, and we can have any other value after that. So remember, this is how I write a domain if I'm trying to just exclude just a couple values. All right, so there's domain. Factor the denominator, find the zeros, leave those out, so parentheses, not brackets, unions in between. Intercepts. So we've got x-intercepts and y-intercepts that we need to talk about. Our x-intercepts are going to be the zeros of the numerator. So to find my domain, I needed the zeros of the denominator. To find the x-intercepts, I need zeros of the numerator. So we are going to factor the numerator, and then we will find those zeros. For our y-intercepts are f of 0, or when you sub in 0 for x. This is going to end up being the same thing as the ratio of the constants. So let's look at this first example here on the left. When I factor this in my numerator, I'm going to get x minus 4 and x plus 2. I can factor the denominator. We don't necessarily have to, but that would be x plus 5 and x minus 3. So my x-intercepts, remember, I am just looking up here. X equals 4. X equals negative 2. So my x-intercepts then, when we write intercepts, you write them as ordered pairs. X-intercepts are going to be 4, 0, and negative 2, 0. For the y-intercept, we're going to substitute 0 in the place of x. So I would have 0 squared minus 2 times 0 minus 8 in my numerator. In the denominator, I would have 0 squared plus 2 times 0 minus 15. So obviously these pieces are going to go away. So I'm going to have negative 8 divided by negative 15. Negative 8 divided by negative 15 is just going to give me a positive. So my y-intercept is 0 and 8/15. Looking over at this other example here, remember I need my zeros of the zeros of the numerator in order to find my x-intercepts. But this is not written in P over Q form. So I can either rewrite this in P over Q form, or I can set it equal to 0, because in x-intercepts the y part is always 0. So if I substitute a 0 in for y here, I would add 2 to both sides. That would give me 2 equals 4 over x plus 3. From here, I could multiply both sides by x plus 3. That would give me 2x plus 6 equals 4. 2x equals negative 2. So x is negative 1. So my x-intercept would be negative 1, 0. And then my y-intercept, if I put 0 in the place of x, putting 0 in the place of x would give me 4/3 minus 2. 4/3 minus 2 would give me negative 2/3. So my y-intercept is 0, negative 2/3. All right. Up next, removable discontinuities, holes. So we're going to set any common factors that the numerator and the denominator have equal to 0. So I'm going to need to factor my numerator and my denominator. So my numerator is going to factor to be x minus 2 and x minus 4. My denominator here factors to be x plus 6 and x minus 2. Notice they have x minus 2 in common, so those would end up canceling out, but that's what I need to take and set equal to 0. X minus 2 equals 0. So the x part of our removable discontinuity is 2. And then we still need to get the y part, because remember, we're leading into graphing with this. So we want to find the y value for that removable discontinuity, which is going to be our limit at x equals 2. So I'm going to take 2 and substitute it into what I have left over after I cancel out that removable discontinuity. So I have 2 minus 4 in my numerator. Down in my denominator, I have 2 plus 6. And this is, again, for the y part. And so that's going to give me negative 2 over 8, which is negative 1/4. So the limit at x equals 2 is negative 1/4. That's the y value that is approaching. That is where our hole, our removable discontinuity, would be. All right, we're going to spend the rest of our time now talking about asymptotes. So vertical asymptotes first. Vertical asymptotes are going to be things that make my denominator equal to 0. Now this would be after you have removed any holes or any removable discontinuities. So you have to get rid of your holes first. We don't need to worry anything about the numerator, so I'm just going to recopy that here. Then we do need to factor our denominator. So multiplies to 15 adds to 8. That's going to be 5 and 3. So that means that x cannot be equal to -5. X cannot be equal to -3. Notice these are the same things that divide up my domain. These vertical asymptotes are going to divide our domain into different regions. So those vertical asymptotes are going to be what x cannot be because of the denominator, because it would cause a divide by 0 error. So vertical asymptotes at x equals -5 and x equals -3. So I would, when I go to graph those, draw those as vertical dashed lines through those points on the x-axis. All right. Then we have our end behavior asymptotes. They can be horizontal or they can be slant. Slant asymptotes are also called oblique. So just as a reminder, our rational function is made up of the ratio of two polynomials, p of x divided by q of x. For our end behavior asymptotes, we have 3 different possibilities. We have the possibility that the degree of p of x is less than the degree of q of x. So the numerator has a smaller degree than the denominator. When this happens, we are going to have a horizontal asymptote at y equals 0. We have the possibility that the degree of p of x and the degree of q of x is the same. When that happens, we have a horizontal asymptote at y equals the leading coefficient of p of x divided by the leading coefficient of q of x. So we're going to divide those leading coefficients in this case. So same degree, divide your leading coefficients. And then our third and final possibility is that the degree of p of x is bigger than the degree of q of x. So the degree of the numerator is bigger than the degree of the denominator. And when that happens, there is no horizontal asymptote. We end up with a slant or an oblique asymptote. So there's our 3 possibilities there. Degree of p of x is smaller, so degree of numerator smaller than denominator, y is 0 for a horizontal. Degree is the same, we're going to divide the leading coefficients. Degree of numerator is bigger, then we're going to have a slant or an oblique asymptote. Let's practice this a little bit. All right, so first we're going to look at when they have the same degree. Then we're going to have the ratio of the leading coefficients here. So both of these are highest power x squared. And so my horizontal asymptote is going to be at y equals 3/4. So since I have a horizontal asymptote on both the left and the right, the end behavior, as x approaches infinity, my function f of x is going to approach that asymptote 3/4. And the same thing's going to happen on the left side. As x approaches negative infinity, my function f of x is going to approach that horizontal asymptote. All right, let's look at the next example over here. First thing I notice about this is that this is not written in p of x over q of x form, so I need to get it into that form first. So I need to give it a common denominator. So I'm going to have minus, and then this is 4 times x plus 2 over x plus 2. So when I distribute and I combine like terms, I have 3 of x, or sorry, not 3 of x, 3x minus 4x minus 8 over x plus 2. And then I would have, sorry, that'd be negative x minus 8 over x plus 2, and now I can compare those leading coefficients. Positive 1 divided by negative 1, so now I see where my horizontal asymptote is. So my horizontal asymptote is at y equals negative 1. So both to the left and to the right, as x approaches infinity or x approaches negative infinity, my function f of x is going to be approaching negative 1. All right, let's look at when our functions are bottom heavy, so different degrees, not equal degrees. So bottom heavy with no constant added, that means y is going to be 0. So that is the situation here. If you think about it, it makes sense because this is 0x squared plus x. So then if I do the ratio of the numerator to the denominator, when I'm comparing equal powers, I have 0 over 1. So my horizontal asymptote would be 0 here. So thinking about that end behavior there, as x approaches infinity on the right, my function f of x is going to approach 0. As x approaches negative infinity, so the left side, my function f of x is also going to approach 0. This other example breaks this rule right here. It says with no constant added. This guy right here is written in transformation form. When it's in quotient form, which is what the first example was, that p of x over q of x form, that's quotient form. This one's written in transformation form, so k, this piece right here, is going to be my horizontal asymptote. You might be wondering why that is or how that can fit with what we've talked about before. So let's look at that real quick. And the reason for that is because if I put it back into quotient form, so I give it a common denominator, and I simplify that, I would end up with negative 4x minus 5 over x plus 2. And then when I look at the ratio of the numerator to denominator, because notice I have the same degree now, I would have negative 4 divided by 1. So it's following the same rules as before. Don't actually truly have a bottom-heavy equation here. All right, absolute last possibility, save the best for last, when we have slant asymptotes. We're going to use long or synthetic division to figure out where our slant, where our oblique asymptote is here. So the 0 of my denominator is negative 2. I'm going to divide the numerator by that. I've decided to use synthetic division here, so I'm going to drop my first coefficient and then multiply and add. That's going to give me negative 1. And then again, I multiply and add, and that's going to give me 5. That's my remainder, but what I'm really after is this right here. That's my slant asymptote. Numerator started off as a second degree polynomial, so this is going to drop a degree. This is going to be a first degree polynomial, so that's just going to be x minus 1. So my slant, my oblique asymptote, will be at y equals x minus 1. Now, we've talked about the end behavior for the horizontal asymptotes. With the slant asymptote, I'm looking at the end behavior for this. This has a positive slope. So as x approaches infinity on the right-hand side, if you have a positive slope, f of x is also going to be increasing towards infinity. And on the left-hand side, as x approaches negative infinity, my function is going to be pointing down. It's also going to be approaching negative infinity. So looking at the exact same types of things that we did when we were talking about odd and even functions and our end behavior, I want to know the end behavior of my asymptote. That will be the overall end behavior of my function.